Let me begin with a word of prayer. So, Dearly Father, we thank you for this day. Again, Lord, I thank you for these students, and I just pray that you'd help us to use this time wisely, Lord. In your name I pray. Amen. All right, so you guys said to look at the fixer, so I'll try to do that right quick. That was 3 point, what was that now? I've forgotten now. Oh, 8. 8.3, number 19. Now, I probably should just put it up here. So we're thinking about X, in his language, a G set, right? And then, which means, for example, how's it go? G dot X is what? Well, that's not. Yeah, we should say G dot little x. This is the orbit of X, right? And then we also talk about the stabilizer of X is what? G and G, such that G dot X is equal to X again, right? And then the thing we talk about a little bit less is the so-called fixer. Wait a minute, this is not the fixed subset. The fixed subset is X sub F, which is X in X, such that, G dot X is equal to X for all G and G. That's the fixed, so like I said, the fixed subset of rotations on the plane was just the origin, for example. But the fixer is something else. Where is the fixer? You said 367, it was there somewhere, eh? In general, if X is a G set, then the kernel of theta is normal in G, and it's given by it says kernel theta is, he says A in G, such A dot X equals to X for all X in X. This is called the fixer of the action. Oh, that is another flavor choice, isn't it? Let me see here. I'm going to try to understand that. This theta is the homomorphism that corresponds to the action, right? Like that we talked about. Theta is a mapping from where? Is that right? G, it's from G to permutations on X? Okay, so this is the, this is his note. So his S sub X is not the stabilizer. That is actually, I would call that perm X. It's a play on the notation. So like Sn is permutations on numbers 1 through n. So Sx is the permutations on those things. It's the symmetric group on the elements of X. But I call it perm because it's hard to not notice that. But how is theta related to the action? Remember we said theta of A, right, of X is equal to A dot x. And that gives me a element of x again. And so there's this interplay between the group action and permutations, and that's the interplay. And then, of course, the kernel of theta I mean, this would mean that theta was the what? It was the if theta of A is the identity, right, on x, then that would mean that A is in the kernel. A is in the kernel of theta, and so being in the identity, that's this condition, right? I mean that. Okay, so this is the fixer of the action. And then in number 19, the part you guys are not confused about was what? That the center is a subset of the fixer. That made perfect sense to you. All right. So he says, let me write it out here. Section, what is it? So he wants to look at the conjugation action, right? So let G act on its set of subgroups, is it? Or set of subsets or subgroups? All right. No, subgroups. Set of subgroups. So x is equal to the set of subgroups. It's okay, set of subgroups of G. And the so if we have H in X, then like G dot H is equal to GH G inverse. This is the action, right? And I guess you're supposed to show that that's an action, but I'll leave that to you guys. And you're supposed to show that the center of the group is a subset of the fixer. He calls this thing F. Okay. Fine. So if the center of the group is supposedly a subset of the fixer with respect to this conjugation action. All right. So to be in F, what does it mean? F is a, so if G is an element of F, what's that mean? Right, so here that's G dot H equals to H, right? For all H and X. I'm using H as a generic subgroup because it seems right. Which of course is to say that what? G inverse is equal to H again. Right? So certainly I mean, if G commutes with everything, so if G is in the center of G, right, then if you look at GH G inverse, point-wise, that's what? That's GH G inverse such that H is an H, right? But if G is in the center, you can commute, and that's just H G G inverse, H and H, which of course is just H again. Now, so you wanted, but you were looking, you wanted an example of a group where, see, all of the examples you look at, the fixer ends up just being the center. But he wants you to find an example of a group where, for this conjugation action, the fixer is not just the center of the group. So it's got to be a non-abelian example, right? Because if it's an abelian, then the center is the whole stupid group. So that's not encouraging. So it's got to be non-abelian, this example we're looking for. Have you tried D3?
Thought about it, but I hadn't actually.
Let's try D3. That's the easiest thing to do. And what are our subgroups? Of course, you've got 1. You got D3. You got the one with A in it. You know. You got your B. You got your BA. You got your BA squared. I think that's it. The ones in here which are normal, abnormal. And I don't know, for some reason we don't use that terminology, but it'd be funny if we did. So we're just not willing to, we're like, judge not lest you be judged. And you're like, yeah, we're just not going to go there. Let's see here. So that must be the reason. So Christian mathematics. Sorry. Let's see here. All right, I got to wrap my mind around this fixer idea here. What do we want? What's the center of D3? I mean, we're trying to compare against that, so we better figure out what that is, right? I'll get you started. 1. Ah, you already got that. But AB is not equal to BA. So A is not in there. And A squared, B is equal to AB. A and A squared do not commute with B. And I don't believe that the B's, I mean, that's it. So the center is just this, right? Yeah. What is the fixer of the conjugation action on D3? So what do we need to be? For G to be in the fixer, yeah. We need G, H, G inverse to be equal to H again for all of these. It's for all H that it has to be. Yeah, we're looking for specific G. How about like B? Is B in there? Is B, H, B inverse, which is B? Yeah, it's annoying, isn't it? Is the I know, it's very, very frustrating to me. I'm going to bring in my own set of blinds and fix this thing pretty soon. Is the pole down there at the bottom has been disconnected again?
Yeah.
Dang it. Why did somebody take that out? Like, who undoes that? You know what I mean? Like, it took us a lot of time to get that up in there. Somebody just undid it after us. Like, why would they do that? Oh, here, I've got an easier solution.
Just move the camera.
Yeah.
Okay.
All right.
Yeah, I don't think we're making any progress.
We can either go that way or this way. I think I'm going to go this way. I believe that ought to do it. You might have to resume or something a little bit, but. All right. I want to say B might be in there. I mean, B inverse is B again, right? Let's see here. So just think about elements, all right? So what happens with B1, B? We get B squared, which is 1. How about BAB? We get, oh, shnikes. We get B,
Oh, no.
oh, man. But maybe that's okay. That gives me BB a squared, which is a squared. That might be okay though. The only sub.
It's also in
Exactly. So that's not going to be a problem where A appears, right? Because wherever A appears in a subgroup, A squared also appears. So that's okay. It doesn't have to. The conjugation of the element doesn't have to fix, but it has to. Oh, it has to fix the subgroup. Fixer. Yeah. Okay. So it's almost like the terminology makes sense. That's your BA squared B is BBA. So if you got A squared, you also have to have A in the subgroup, but good news, we do. The ones I'm worried about, of course, BBB is B, so good there. And the BBA, B, is, uh-oh. Yeah, that's AB, which is, yeah, BA squared. Dang it.
So that means that, oh yeah, BA squared and BA would have to be in the same.
That is a deal breaker because that means, for example, that BBBAB, BBB, this guy is not equal to this again, right? Because this does not have BA squared in it, I don't believe. I really thought B might be in the fixer, but no. Is A in the fixer? I feel like if B's not in the fixer, then BA and BA squared are also going to be, they're also out. Maybe A though.
But does it matter if A is in it? Because A is also in the...
Definitely this is okay. We're good there. That one's fine. The 1 is fine. D3 is fine. It comes down to these guys, you know, is A, B, A inverse. So that's A, you got 1, you got B, right? And A inverse is A squared. So you're looking at A squared, A, B, A squared, which is 1, good. And this one, jerk. That's B, A squared. Yeah. Which is not what I want. Because that's not equal to... I don't know. Try the quaternion 8 group. Maybe that one will work. Anyway, does this illustrate the thought process? Yeah, you win some, you lose some. All right, so let's try Sylow example. So I think example 7 I have not covered in class yet. We're going to use example 7 hopefully as a jumping point jumping off point for perhaps doing number 7. Was number 7 in the training? No. Is, okay, so good. So example 7 is, it says, show there's no simple group of order 56. All right. So I guess if we say G, the order of G is equal to 56, we notice 56 is what, 7 times 8, or 7 times 2 cubed, more to the point, right? So the number of, what's this mean? He says, so the number of Sylow 7 groups must divide 8, and the number of Sylow 7 subgroups must be congruent to 1 mod 7. This is from Sylow's third theorem, I believe. And so you think about, so, you know, we need a divisor of 8, right? Which is what? 1, 2, 4, and 8. And which of those are congruent to 1 mod 7? Oh, yeah. 1 or 8. Oh, yeah, that's what he says. Okay, good. I thought I just saw 1 when I looked at it a second ago. I was like, what rules out the 8? Nothing. So n number of Sylow 7 groups is either equal to 1 or 8. Good, you guys are thinking, even if I'm not. Great. All right. So he says, if the number of Sylow 7 groups is 1, then that means that the Sylow 7 subgroup is normal, right? Does that make sense? Why is that? That's one of the other theorems we found in this section, which is that if there is a unique Sylow P subgroup, then it's normal. In D3, the cyclic subgroup generated by A is normal because that's the unique Sylow 3 subgroup. In contrast, the B, the BA, and the BA squared, these are abnormal because they're not unique. I mean, there's 3 of them, 3 Sylow 2 subgroups there. But if there's 1, then that's normal, and that would imply G not simple, right? Because it has a Sylow 7 subgroup, and it can't be, I don't think it can be the whole group, right? So that must be a subgroup that's between the identity group and the group itself, which means it's not a simple group, right? It has a non-trivial normal subgroup. A proper non-trivial normal subgroup. Now, what happens if the number of Sylow 7 groups is 8? It says that then there are 8 distinct cyclic subgroups in G of order 7. How is that? Does that make sense to you guys? I don't know if it makes sense to me yet. If n7 equals to 8, he says then, oh, what does that mean? That means the number of Sylow 7 subgroups, there's 8 of them, right? 8, right? Distinct. I mean, this is just the definition, right? Of what that is, right? And it's and he says they're cyclic subgroups of order 7. How does he know that? So the Sylow 7 subgroup has to be a P subgroup, right? A 7 subgroup, which means every element of it has to be what? A power of an order. Like every element has to have order 7 to some power. It's a subgroup, so it's got the identity in it. And then you have elements which either have order 7 or 7 squared or 7 cubed. You've got 8 distinct subgroups. Think about the counting. They're distinct, so they're not all the identity. They're related by conjugation. We also learned that in the section. So they have to have the same size. I can't have one that's got like more than the others. They have to be sort of equally sized. You can't have something with like order 7. You can't have like 7 squared, an order 7 squared element, because then you don't have enough elements. They have to be order 7, otherwise you can't deal with the 56. If they were higher order Sylow 7 subgroups, then you don't have enough space for that. So they all have to be size. They all have to be, the elements have to be all order 7, except for the identity. So every one of these is a cyclic group of order. He says cyclic because if it's a, I'm missing the words here, but every one of these has to be a cyclic subgroup of order 7. So the order 7, is that right? Sylow 7 subgroup. And somewhere in somewhere in the lead up to this, we have learned that if you've got a oh goodness gracious, when we talked about P groups before, if every element of the group has order a prime, it's got to like follow that it's cyclic. I'm trying to, that's not quite right. So if elements of order 7. So if in one of these subgroups you've got A, and it's in there, right? Then you've also got A squared, A cubed, A to the 4th, A to the 5th, A to the 6th, and then of course 1. That everything in there either has order 1 or 7, right? Because these, if A has order 7, so does that, and that. Because those are all, 2, 3, 4, 5, and 6 are relatively prime to 7. So those are also generators for that. The point is there's 7 of them. And each one of these Sylow 7 subgroups, it can't be bigger than that, again, because we only have 56 to work with. And so how many elements of order 7 do you have? Every one of these Sylow 7 subgroups, of which there are 8, picks up how many? 6 elements of order 7, right? So that says that in total, you've got 7 times 8 equals to, not 7 times 8, I can't do math. 8 times 6, right? Duh. 48 order 7 elements, right? And what else do you have? Your group of order 56, right? So what's left over is the identity, of course, and elements that are not order 7, right? So the other thing that's left over is the order 2 things. So this implies that there's the Sylow 2 subgroup has how many things? 8 elements, right? And because there's a 2 cubed in the order of the group, that's got to be the unique Sylow 2 subgroup. So that implies that n sub 2 is equal to 1, which implies that, let's call this thing H. H is unique, and H is a normal subgroup of G, and it's not equal to. Therefore, G is not simple. So in either of the cases, either the number of Sylow 7 subgroups being 1 or 8, either possibility, which is everything, were led to the existence of a non-proper, non-trivial normal subgroup, hence G is not simple.
H is normal G or H is not?
Oh, my bad notation here. Perhaps I should say this. How about this? H is normal subgroup of G, and H is not equal to G. There we go. I mean, H has 8 things in it, so it's not G. Okay, I think hopefully this is enough discussion to frame problem 7. Let's try. Let's foolishly forge ahead and try number 7. We're supposed to show that a group G is not simple if the order of G is 40. Oh, why am I erasing this? That was dumb. Suppose the order of G is 40. We're supposed to show that that implies G is not simple. All right, number 7 of section 8.4, which I may not have assigned, but it's still a good problem, yeah? Let's see here. So I guess the question was 40. Which is, what, 2 cubed? Oh, this is the same problem. I think this is literally example 7. Because we're like, oh, all right, so then the number of Sylow 5 subgroups must divide 8, I believe. And 5, I should just erase the 7s and put 5s. And is congruent to 1. Oh, it's a little bit different, isn't it? It actually is a little bit different. I'm sorry. It's actually easier. N has to be congruent to 1 mod 5, right? There's the interplay between 8 and 7 is different than the interplay between 8 and 5. This is easier because this implies that, yeah, the only solution to that congruence is just 1. Because, of course, oh, wait a minute. What are the divisors? Let me think. 1, yeah. So that's good. 2 is not congruent to 1 mod 5. 4 is not congruent to 1 mod 5. 8 is not congruent to 1 mod 5. That's the only solution. Oh, so that's it. So therefore, the Sylow 5 subgroup is unique and hence normal by the theorems in this section, right? I mean, I could be more precise. That's theorem. Come on, where'd you go? Is that not a theorem? I mean, I guess it's kind of theorem 2. If H is any P subgroup of G, then H is a subset of AP A inverse. So if P And, Sylow's second theorem, if G is a finite group, any two Sylow P subgroups are conjugate. So, they're corollary 2. There we go, that's what I'm looking for. Corollary 2. A Sylow P subgroup of a finite group G is normal in G if and only if it's unique. So, corollary 2. So therefore, G is not simple, as it possesses a normal subgroup which is not the identity or itself. I should have assigned this one. I was scared looking at these to start with because I don't, it's not in my blood. I don't have a good sense of when a problem is like that versus when a problem is like that. What's 108? Four times 27? So let's foolishly look at this one. 108, that's 4 times 27, although I think we got the idea across already. I'm just going to make it worse if I find one that doesn't make sense, so I should probably just stop while I'm ahead. But here you would look at the Sylow. Seems like looking at the uncomplicated factors productive, yeah? So I guess I should look at, I'm an idiot. That's 2 primes, right? I told you guys I'm not a number theorist. So, I don't know which way to go here. Want to go with, want to study the 2? Study the 2? Okay. So n sub 2 has to divide 27. Starting to regret that. And yeah, let's weigh our options here. We got to look at n2 divides 27, and n2 is congruent to 1 mod 2. Yeah. Sorry, I can't remember my math. Or we can solve n3 divides 4. And n3 is congruent to 1 mod 3. Yeah. I think I'm going to go with door number 2 here. Yeah. So the divisors are 1, 2, and 4. 1 and 4. Okay, so n3 equals to 1 or n3 equals to 4. If this is the case, that says that the Sylow 3 subgroup is normal, and that implies that G is not simple because that wouldn't be the whole subgroup. All right. On the other hand, if n3 is 4, what's that say? Let's see here. G has a lot of wiggle room, though. The order of G is 108. So I'm sorry. The number of Sylow 3 subgroups. D3 let me down today. It's usually good for what ails you. Not today. Sorry, I gotta actually think.
Did you just do the other one too and see how many Sylow 2 groups there are?
Yeah, that's, it might be. It could be we have to meet in the middle with the data. That seems possible, but I'm just trying to just wrap my mind around what does that mean. I have 4 Sylow, 3 subgroups, right? They have to be distinct, except for, of course, they always overlap with the identity, right? Like, you can think about them like this. Right? They have to be the same size, but they overlap with the identity. And so, I'm trying to, what's the structure of a Sylow? They're P subgroups, right? What's that mean? I think it means that every element of the subgroup to some prime power is the identity, right? I'm trying to think. It doesn't have to be the same prime power. I mean, for example, if you have everything, how to say this? Words. Let's see here. 80's got 3 primes in it. Interesting. I mean, suppose they were, if they're like the ones we were looking at in the last example, if they're just, if they're, I'm missing a word here, guys. If all of the elements of the subgroups raised to the 3rd power is 1, then they each have just 3 things in them. And I think that would only give us, is that going to work? I mean, then you'd have a total of 3, 2, 8, 9 elements that would leave you with, 8 non-identity elements, right? So that leaves you 100 of what's left. Can we have 100 elements that are all part of the Sylow 2 subgroups here? I mean, is that conceivable? Maybe it's conceivable. Let's do what you said. Let's think about this. N2 has to divide 27, and we need that N2 is congruent to 1 mod 2. So like you said, let's face the music. What does that actually give us? You say 1, 3, 9, 27? Oh, I'm sorry. It's not as bad as I was thinking. I'm an idiot. And so which? Oh, yeah. They're all congruent to 1. So they're all possible. So we can either have N2 as 1. We can have the number of Sylow 2 subgroups as 3. We can have the number of Sylow 2 subgroups is 9. We can have the number of Sylow 2 subgroups is 27. There's something about Sylow subgroups I'm not taking advantage of here to make this problem workable, right? It may be that if I study Oh, we haven't looked at example 8 yet, have we? Let me look at that for a second. So there you've got, oh, it's very similar to this. It's 2 cubed times 3 squared. So there we have n sub 2 is 1, 3, or 9. N sub 3 is 1 or 4. The method of example 7 fails. All right, well, there you go. However, let P denote any Sylow 3 subgroup of G. If N3 is equal to 1, then P is a normal subgroup of G. We're done. If N3 equals to 4, then, so let's see here. Try to follow this here. P, any Sylow 3 subgroup, right? That's what he says. So if N3 equals to 1, we're good. So N3 equals to 4. Then what's that say? And N3 equals to 1 means that P is normal, right? But if N3 is equal to 4, then the index of the normalizer of P is equal to 4. That's the thing we're not using yet. The normalizer of P. Well, it's equal to 4 in that example. What's it equal to here? Is it still, is it because that's 4, or is it? Mike, is that 4 because Sylow's third theorem? Yeah, that's part 3 of Sylow's third theorem, is that the number of P, Sylow P subgroups is the index of the normalizer of P. So this is 4. So what's that? What does that tell us? Ow. So it gets that. So homomorphism from G into the symmetric group of order 4 with the kernel of theta, a subset of the normalizer of P. And he says the kernel of theta is not equal to 1 because the order of G72 does not divide the order of S4, which is 24. As the kernel of theta is a normal subgroup of G, and the normalizer of P is not G, we are done. Okay, so we follow, basically, so I know we're out of time, so I'll just say, to do this, to complete the thought, follow the method of example 8. So which says that there's going to be a homomorphism from G into S4. I think it's based by I think it's based on the conjugation action. This idea is the homomorphism theorem paired with the conjugation action and the fixer. Well, that's not anyway. That example 8. Because S4 has got 24 things, but G is what? Order theta is what? Theta is going from G to S4. So it's pretty simple. G has 40 things in it, and S4 has 24 things in it. So this map has to have non-trivial kernel. It's got to send more than one thing to the identity, and consequently, The kernel and then the kernel is a normal subgroup. Because there's homomorphism, the kernel is a normal subgroup of G, which is not everything. So, yeah. So we have not been, the thing that we have not yet properly embraced is part 3 of Sylow's third theorem, which is a slightly more nuanced tool than example 7 was. That was just, even though my state of tiredness, I was able to understand that today without a lot of effort. This requires us to go back and understand the extended Cayley theorem homomorphism idea and to use it to do something. So anyway, I shut up. Thanks, guys.